Welcome to this ISN podcast. My name is John Feehally, and this morning I'm in Oxford in the UK, and I'm pleased to say that here with me is Professor Sir Peter Ratcliffe. As some of you will know, Peter is a nephrologist, and many of you will also recall that a few weeks ago, Peter, along with two other scientists from the United States, was announced as the winner of the 2019 Nobel Prize for Medicine, a prize given to them for their discoveries of how cells sense and adapt to oxygen availability. So, Peter, firstly, many congratulations.
Thank you very much, John.
On winning the Nobel Prize. And thanks for making time to talk to me today. I'm sure you're flooded with interviews over recent weeks. And welcome to all of you who are going to listen to this podcast, wherever you are in the world at some time. And I hope that you enjoy listening to the conversation that Peter and I are going to have. You'll be pleased to learn more about Peter, about his remarkable achievements in science, and maybe we'll hear some lessons about how to build a research career, how to combine being a clinician and a scientist, and how to build a research team. In his case, a research team which really has changed our fundamental understanding of biology, and also how to combine being a researcher and a clinician and having many other leadership roles in British medicine, as Peter has had. So, Peter, thanks very much for talking to me. Can we start early on? Why medicine? Why did you go to medical school in the first place?
Well, that one I have spoken about quite widely. I did not make the decision in accordance with the usual rules that we apply to our student admission in Oxford, I'm afraid to say. It was a little different in my case. I wanted to study chemistry. Not completely sure why that was. I was quite good at it at school, I think. And a distant relative had been a successful chemist, and it was told to me that I should follow in Leslie's footsteps to be a chemist. And I was in the chemistry department, and this, I think, is broadly true. The headmaster, John Lorraine Spencer, M.A. Cantab, a sort of glacial figure who wore a gown, came into it was a boys' grammar school, not a fancy school, Lancaster Boys' Grammar School, Lancaster Royal Grammar School. He came into the chemistry lab and said, Ratcliffe, could I have a word? And I, of course, said, yes, sir, and followed him out of the room. And he said, Ratcliffe, I think you should study medicine. And he wasn't the sort of guy you challenged, so I said, yes, sir. And we went back into the study and we crossed out the word chemistry and wrote medicine on the application form. I really don't know whether he thought that I would be good at medicine or bad at chemistry. I've never understood that. But that put me in medical school.
Right. And from the beginning in medical school, were you always interested in research? Did you always think you would be a researcher as well as a clinician?
No, I was ambivalent. There were other distractions at medical school. I was interested in the social side of things. I never really got to grips with it at all, certainly not at Cambridge. I think I was fortunate in not being clever enough or mathematically inclined enough to do what was rather prevalent. I worked in the physiology lab, and the brightest people were engaged with better mathematical descriptions of the nerve action potential or the muscle action potential or excitable tissues, which the great and the good then in Cambridge was engaged with. I wasn't clever enough to do these complex differential equations, and I had to carry on. So it wasn't an immediate connection with research. I think that's fair to say.
And having qualified in medicine, why nephrology?
That was because Larry Baker said I should do it. I can be clear on that. It was Larry said it's a great specialty, and you'd be good at it, and you should do it. And I like the headmaster, but Larry's a different sort of figure, very helpful to me. I said yes without really giving it
But nevertheless, you must have enjoyed nephrology, and there must be something that tweaked it for you.
But I enjoyed a lot of things that I've done, and wanted to. At the time, I wanted to be a psychiatrist. Time I wanted to be an obstetrician. Does as a medical student, and I did the house job in medicine at Barts with Larry on the nephrology side, and yes, I could see. I could see there were real things to do in nephrology. There's a point in being a nephrology specialist because there was specialist medicine, and that wasn't completely true of all the specialities at that time.
Mm-hmm. And then your nephrology you'd been Cambridge and then Barts in London, but then your nephrology training was here in Oxford. Is that right?
That's right. I did the house job, and then I came here after my SHO jobs, which did not involve nephrology, to do nephrology in Oxford.
Yeah. And here you are still in Oxford. Is that right? You've been here throughout that time?
I still am in Oxford, John, but in a different guise.
Has it been an important advantage to be at a university like Oxford, do you think, Peter, for what's subsequently happened for you? For sure. In what sort of ways, for those who don't know Oxford so well, listening from other countries, for example? I
think there were two entry points, which I've talked about before, but I'll just emphasise, if I may. It was an unusual entry to science. The nephrology bit wasn't quite as straightforward as Larry has said. Some people were not as encouraging as Larry. They said, you'll be lucky. There are only going to be two jobs between now and the year 2000. This was about 1979. And, you'll have to get one of them. So you'll have to distinguish yourself in some way. And that led me to make case reports. You might have done that yourself, John. We looked at patients and thought what lessons we could draw from observations that had been made on them. I think that was very important in the scientific training, actually, since it taught two things. One, how to draw conclusions from a fixed data set. And that's important that in design of experiments that will come to completion, and often is not the case in people who are in my lab as postdocs. They've often gone and on doing more experiments, but they have to come to a conclusion. Case reports tell you how to see that. It also taught me to look across an array of research possibilities and select things. And that was important because it enabled the selection of the question. And that is completely key. But your question was about Oxford. Why did it matter? And the answer is that once you've selected a question of your own, then you require some level of technical competence. And I had to enter molecular biology to do this. And what I've said is you need a friend with a laboratory to do that. And I had two, in fact, John Bell, who took me into his laboratory, and David Weatherall, who had the institute in which John's laboratory was placed, who took me into his institute. And frankly, if that hadn't happened, there was no way I could have entered the molecular analysis, even if I got the question right. So it was key.
Yeah, understood. Key. Okay. Now, when I first met you, which I guess is probably 35 years ago, you were studying what we used to call acute renal failure and looking at the metabolics of it, I seem to remember, with NMR spectroscopy.
Yeah.
So why didn't you stay in the AKI field? What was it about the oxygen question that really attracted you, made you think it important?
I didn't think I could solve the AKI field in the way that I'd intended to solve it. I did not think that phosphorus NMR signals could be either diagnostic or mechanistically informative in the end. The kidney's heterogeneous and one or two cells might matter, so measurements on the whole organ won't inform the question. But it did lead me to think about the kidney circulation and what it might be that enables the kidney so precisely to control EPO in accordance with hematocrit, but not kidney blood flow. As you know, that's not a stimulus to EPO production. I didn't solve that problem either, but it did draw the attention to EPO, and then of course we settled on the question: is what is the mechanism, the molecular mechanism of oxygen sensing?
And when you started thinking about these questions, this was relatively soon after EPO had arrived in clinical practice. Is that right? I mean, the original papers were...
I started in 1989.
Yeah.
So it was a buzz about EPO in the nephrology field at that time.
I mean, I know this is almost impossible, but how about trying in 2 or 3 minutes to describe to me how you got from the first question to the much more fundamental things that have emerged? I appreciate it's putting a career of work and a Nobel Prize into just a few sentences.
Well, there were 2 bits to the work, really. One was, broadly speaking, the discovery of the system. At least that's what I want to call it. And the second was, how does the system work? So that discovery was quite important. We identified control sequences at the EPO gene, and that was the first step in moving from how EPO was controlled to the oxygen sensing mechanism. We then transfected. We put those sequences into other cells that had nothing to do with making EPO, and to our surprise, they still worked. And that was a major transition. That is the source of the rejection letter from Nature that you see on the wall there. And that changed the whole thing from what was believed to be a private and somewhat quirky aspect of kidney physiology into a mainstream physiology problem that affects vascular function, cancer, metabolism, all the things you've heard about. So that was a transition. Yeah. And try and give me a flavour of what the implications of this then are now. So in the real fundamentals of this oxygen sensing system, if you were a clinical visionary over 20 or 30 years, where do you expect this might take us? Well, that's a question that I'm not going to answer.
I thought I'd try.
Now, the important thing about the Nobel Prize, they hedge their bets. It is the Nobel Prize in physiology or medicine. And actually, we don't know which at the moment. Well, we do. We know that I believe this is an advance in physiology. I believe that the mechanism is correct. It probably came along with the evolution of animal life 500 million years ago. And if we're still going in 5 million years or whatever, it'll still be the way we work. So it is, in a sense, an eternal truth. And that's what's so satisfying about this type of work. Now, the clinical side, the medical side, is contextual. And that depends on what other competing medicines, what standards of safety are set, and what diseases we want to treat. These new drugs will induce EPO, and they will correct renal anemia. That's for sure. And they are licensed for that, as you will know, in China and Japan now. The question for the medical community is, how will we be in 5 years' time? Will they have additional actions that are safe and beneficial, or will they have unwanted effects which are difficult for patients to sustain? The real problem is that EPO is not a bad drug for kidney anemia. So you can argue about that, but it's not too bad. Yeah. So beating it or even equaling it is not completely straightforward, and that's the issue that's under consideration. Yeah.
Can I turn to some more general aspects of how one gets on with research? So you start with your own laboratory, but then within a short time, you're bringing into your lab bright and good people to work with you. And I'm very interested in how easy it is to spot those people, because there must be many people who want to come and work with you, but some of them have been real stars. And how does one identify those?
Well, I think I was very lucky there, and that was an important thing of being in nephrology in Oxford. It's essentially other people identified them for me and brought them. So people like Chris Winnells, like John Leddingham, like David Weatherall, John Bell, all recommended, I think, my lab to other people who were very clever and very important. Chris Pugh, Patrick Maxwell, Shortran Tan, Ben Ebert. They've all done very well. And this was the team, Johnny Gleadle in the US, in Australia rather. They were the team that powered it up in the early years and were very important in getting us going.
And for you, I mean, there are some researchers who still love it, even at a senior stage, going into a laboratory or sitting at a computer for hours looking at raw data or going into the lab and doing experiments. Are you that sort of person, or are you always being the person who drives the ideas and lets others do the practical experiments?
No, I'd love to be that sort of person. I've never been that good at it, and I certainly am not now, as I had this rather fond idea that taking up the job at the Crick, I'd go back to the bench, but I just haven't done it at all. And frankly, I think I lack the concentration. I think I would claim still to have an imagination, but the thing that faces a bench researcher is having that imagination and also being capable of being extremely focused and accurate. And there's a counterpoise in those two human attributes. Yes. I don't have the latter. I no longer have good concentration that I can pipette out 30 aliquots of 5 microliters without any chance of error. And that as you'll know, is fundamentally important.
But the issue of imagination is interesting, because you're looking at data and yet having to, in a sense, be imaginative about how you interpret them or what you make of them. So when you, particularly for you, with that pivotal moment when you discovered that this was a system not just in kidney cells but in other cells, I mean, there might have been a moment where you might have shrugged your shoulders and thought this isn't important, or was it absolutely self-evident?
We thought it was a nuisance at first. The actual experiment that we wanted to do, and I still haven't done, I'd love to do a really intelligent expression cloning experiment. This is where you take the genes from one cell that has a property that you're interested in, and you transfer them into a cell that doesn't have that property. And in doing so, you identify the genes that encode that property. And that's what I wanted to do. So we were testing the recipient cells to make sure they didn't have the property, otherwise disqualify the experiment. Yeah. And what we found is that it did. Yeah. So I was concerned that, well, obviously that disqualified my plans. And we were slightly puzzled, taken aback, wondered whether this was some sort of non-specific thing we were looking at. But eventually came to the conclusion that actually probably very, very important.
And did you have to do that experiment several times to convince yourself it wasn't a mistake in the experiment?
Yeah, we did.
Quite a lot of times.
Quite a few times. Yeah. Patrick Maxwell did it quite a lot of times.
So, Peter, somehow or other, you've done this work and won the Nobel Prize, and yet you've still seen patients, and you've done all these leadership management roles that one has to as one becomes older in medicine. How did you balance all of that? I mean, how do you work through that without working yourself to death, to be frank?
Well, I fear by not being terribly fair on some aspects of the work. First of all, to be clear, I did not do nephrology when I did the management role in running the Department of Medicine. And the reason for that, people will, in this audience, know that nephrology I still see as the most demanding clinical specialty, in that it requires the immediacy of high intensity intensive care medicine, and also the issue of pastoral care. So I had to give it up with the experience that the lab rang me to where your patient's potassium's 8.7. I just thought you'd like to know. And I might be conducting an interview like this. I could no longer ring up the registrar and say, would you please sort this out? Some action was required immediately on my part. So that was inconsistent with the headship of department, and broadly inconsistent with with the lab at this level. So I changed and did acute general medicine, where I could see patients, perhaps unfairly, without taking much pastoral responsibility, doing the technical aspect of diagnosis, teaching diagnosis. Quite enjoyed that. It's possible to do it for a defined period of time and then step away. Whether that's actually fair on the patients, I'm not so clear, but it's easier to do that in general medicine than in nephrology, as people will be aware. The management of the Department of Medicine, well, that's a difficult one. I did the minimum consistent with it not actually disintegrating, and that might actually have been a good thing. What we noticed was, what you will notice, is that the most badly behaved members of the department are often the most productive. They're not reasonable people. Reasonable people don't discover things. They don't discover the North Pole, the South Pole. They don't walk across the Antarctic. Nearly all discoveries done by unreasonable people. So an element of benign neglect is usually has some advantages in a productive department. I think the department was productive. It was certainly neglected in the sense of hands-on management. I just didn't do it. I didn't have time, and I would argue the department didn't suffer for that.
I'm not quite sure how to ask this question, but throughout this period of research which you've engaged in, what were the things that most surprised you, either about the way things did or didn't happen, or the way the science went? I mean, if you look back now and think how your career and it's all developed, what surprised you most?
Almost everything surprised us. It was a surprise that the system was widespread in all human cells. It was surprising that it was in animals, that primitive animals that don't have a blood system or kidneys or other organs. It was then a surprise that it wasn't in yeast and plants and prokaryotes. The mechanism was a surprise. Practically every type of ferroprotein had been suggested, except the type of enzyme that we ultimately found. It was a surprise that the solution was as clear as it was. I think it is a solution. I think there are defined enzymes. They're the only enzymes that do it. And people had all sorts of ideas about the complexity of oxygen radical biochemistry, which wouldn't have been soluble in the sense that of defining an enzyme that was it's a perfect drug target. Uses oxyglutarate as a co-substrate, so you make drugs that look like oxyglutarate and mess it up, and you make a drug. So all of that was completely unforeseen and very surprising. And that's part of the good fortune sometimes of research.
Finally, remembering that many people listening to this are not from the UK, and just explain to people what it means when I introduced you as Sir Peter Ratcliffe, and after your name the letters FRS appear, which do not often appear after physicians in this country.
The Sir bit, that's a great honour, conferred by Her Majesty. In my case, it was conferred by the Princess Royal. She did it rather nicely at Buckingham Palace. And this is something that we treasure in the UK, like many traditions. It's rather nice. It actually doesn't make very much difference to the way most people treat you. Perhaps it's quite good for an opera ticket, but in most cases, people carry on regardless.
Doesn't increase your chance of getting a grant, for example?
I fear not. No, it doesn't do anything there. The FRS, well, that might. That's the Royal Society, of course, one of the world's oldest scientific societies. That's a great honour, and that probably has some kudos in scientific circles, but again, whether it can buy you a better opera ticket, I don't really know.
Peter Ratcliffe, thanks very much for talking to us.
Thank you very much, John.